G'day and welcome to episode 8 of 7 Wrangling. Thanks for sticking with it this far. I hope you've been enjoying the content and the insights as we go through this first phase of the project, which is building this MK RX5. This is the third part in the 3-part series, all around the chassis strengthening and analysis testing that we did. Episode 6 was all about going through the process of testing the chassis and putting some science behind our measurements, making sure we understood not just how much it was twisting, but where it was twisting. Episode 7 then nailed down exactly where it was twisting and went to the trouble of strengthening the chassis in those areas, and then we retested at the end of that and came up with a significant result, about 230% stiffer than the baseline, which was all I needed for me to pass the or achieve the requirements here in Australia. So here we are at episode 8, and what I wanted to cover today was mostly around the question of why. Why does a stiff chassis matter in any car, or a race car for that matter? I think intuitively we think it probably should be stiff. We probably experience old cars, if you go over a big enough bump and the doors fly open. Things like that. Most modern cars today are actually very, very stiff and very, very strong in comparison to the same type of car maybe 30 years ago. So we're all a lot safer for that, and they probably all handle a lot better too. But the question is why? Why is a stiff chassis better for handling than a soft chassis? Now, I'll state right from the start, I'm only just scratching the surface on this, and I'm aware of how much I don't know about this topic. So I'll be looking at it pretty much from a high level. Down the track, when we get into the next phase of the project, which is just starting to tune the chassis and to extract as much handling performance out of it as we can, I think we're going to revisit this topic again when we start to look specifically at components of the car and start to analyse it with some maths behind it. But for now, I think probably just taking a look at the surface of this topic is probably all we need to cover. Generally, we look at suspension systems on a car as being the rear suspension system or the front suspension system, and we often don't think about them combining together as being one suspension system. We might, but it's not often you hear people talking about the left-hand suspension system in a car and the right-hand suspension system. It's nearly always front and rear. And that concept probably works fine for the most part, right up until you need to start extracting the maximum amount of grip out of your tyres. Until you start to get into that last maybe 5% of traction, 10% of traction, for most people, that will never really be a problem. The overall function of a chassis is to keep everything connected and keep wheels pointing in approximately the right direction, or as intended by the person who designed it, as far as they possibly can. And if you jack up say the rear right-hand corner of a car, I think we'd all expect to see the front right corner of the car also lift up as well, which tells us if we apply a load to the rear right of the car, that we're probably going to see some sort of increased load on the front left of the car and decreased load on the front right of the car. I think that sort of makes sense. If we're going to start talking about this a little bit deeper, the first thing we need to cover off is tyres and how they generate grip. So I think most of you would be familiar with the concept of a traction circle, and that a tyre only has so much traction or grip that it can generate for the car. The vertical load on a tyre, as that increases, the grip on the tyre actually also increases as well. But the trick of it is it doesn't do it in a linear way. You can increase the vertical load on a tyre, but as you do that, the grip generation of the tyre starts to tail off to the point where it reaches saturation, and then there's really no more grip. And that's what we all know as a bad ending to the day. So that's tyres. And if we think about not just one tyre, but all of the tyres on the car, firstly a pair at one end. The purpose of the suspension at the rear or the front is to try and maximise the amount of grip between those two tyres by sharing the loads equally amongst them. But if you take 50 kilos of vertical equivalent load off, say, the inside tyre and apply that onto the outside tyre, you don't end up with the same net amount of grip. You end up with less grip. So as often as possible, if the amount of vertical load that just from the car weight and the cornering forces, if they can be shared equally amongst all 4 tyres, that's most likely going to give you the best chance of generating the most overall grip for the car. Back to the topic of where the chassis fits into the middle of all of that, as we agreed before, we know that it plays some sort of role in connecting the front and rear suspension systems and equaling out the overall tyre load forces, or maximising the amount of grip that all of the tyres together can deliver to the car. So if the front of the car and the rear of the car were basically isolated suspension systems, as soon as one of those loses traction or it saturates the amount of grip that can be generated from the tyres, well, that's the end of the corner as we know it. If the front gives way first, we call that understeer, and the car will generally go in a straight line forward or somewhere near that. And if we lose grip at the rear, well, that's generally what we call oversteer, and the car will tend to spin out. Either way, that's as fast as you're able to go around that corner if you reach the limit. So what if we had a chassis that was able to act as an intermediary there and take some of that tyre load, some of that excess tyre force that one end is feeling, and to be able to transfer that to the end of the car that still has grip available that it can deliver? Well, that suggests then, if we could do that, then we would be able to generate higher cornering forces, which means basically get around the track faster. Let's now talk about springs. I purchased a couple of springs, a small one, which I'm going to call the wheel spring, and the large one I'm going to call the chassis spring. You'll see why soon. So what I'm doing here is just testing that wheel spring, just to see what sort of force it develops in newtons when it's stretched over a certain length. Now you can see the chassis spring, which is quite a bit stiffer. And doing the same test, this is all pretty rudimentary. So we're not looking for 10 decimal places here, as I'm sure you can see, but just to paint a bit of a picture about how springs actually behave. Springs are quite cool. Now here we have 2 springs in parallel. So that's the large chassis spring and the small wheel spring operating together in parallel, side by side. And then finally, the chassis spring and the wheel spring in series, so one after the other. And this is actually how they would be situated in the car. Matter of fact, we'd have 2 wheel springs, but let's not get lost in the details. All right, so there we are, all the testing done. Note, so far we've been looking at tension springs here because frankly they're just easier to wrangle than compression springs or torsion springs, but really they just work in the same way. They all, we use pretty much the same equations for them. The only difference is when we talk about torsion springs, because we're talking about rotation, we're really just measuring their movement in degrees or radians of rotation, rather than with tension or compression springs, we're measuring their extension in millimeters or meters. So looking at the graph, the first one we want to look at is the wheel spring and chassis spring combined in series, just as they would be in the car. Now they have resulted in an overall softer spring, as you can see there. In effect, the chassis spring diluted the effect of that wheel spring. As we can see from the picture here, the reason we got that overall softer spring with them in series is because that chassis spring moved a little bit. And that's indicative of our car chassis twisting and not allowing all of the forces to be transmitted from one end to the other, diluting it down. 2 points to note really on that. The softer the chassis spring relative to the wheel spring, the less the forces between the front and the rear of the chassis are going to be transmitted. Also, since all of the mass of the car, nearly all of the mass of the car, all of the sprung weight of the car is actually attached to that chassis spring in one position or another and along it somewhere. Well, the softer it is, the more unreliably that car mass actually gets distributed to the wheel springs and ultimately the tyre contact patch. Now remember, we discussed earlier that with tyres, the maximum traction that we're going to be able to achieve from our tyres is when all of that mass can be equally shared amongst those tyres. That gives us the overall best chance at achieving maximum traction. So I think it really follows then that a softer chassis relative to the wheel springs is going to be less effective at maximising the combined grip of the tyres. Now let's take a look at dampers. All of the discussion so far has really just been on the effect of chassis stiffness and car balance based on the springs, the four-wheel springs and the chassis as a spring. But springs need dampers if they're going to be effective and controlled. Dampers on cars and race cars is an entire field, and people devote their lives to this. And I don't really understand this in any great depth whatsoever, but this is what I do understand. If springs are really concerned with the overall magnitude of the forces between the chassis and the tyre contact patch, well then I like to think of dampers as being more concerned with the timing, as in the ramp up and the ramp down of those force changes between the tyre contact patch and the chassis. So here's something to consider with our wheel springs. And now we all know that with every wheel spring, we've got a damper there to control the oscillations. Whereas the chassis, that has nothing in particular that's been added to dampen it as a spring. Originally I had a whole section here on spring frequency and damping and how it's all affected by the mass and the spring rate. However, it just confused the issue. So I'm going to simplify it right down to, if you've got a weak chassis, it's going to respond more slowly to driver inputs. If you've got a stiff chassis, it's going to respond faster to driver inputs. Let's go back to our original question about why chassis stiffness is actually important to handling. Well, we talked about the effect of wheel spring and damper tuning based on having a stiff chassis and how it can heavily influence that. But there's another significant factor here that we need to think about, more of an organic factor in all of that, which can have a significant effect in handling performance. And that's really the driver, or more precisely, their ability to extract all the traction that the tyres have to give. It's already in there, it's just the driver's ability to actually get that out. So if we think on one hand of a soft chassis that gives, say, mediocre response to wheel spring and damper tuning with a bit of a delayed response to achieving that sort of chassis set. The example, I guess, is the driver inputs some steering, and by the time the chassis really started to respond to that, the driver has already got impatient and decided that more or less of what they gave the first time is required. They input another signal into the car with some steering, and the chassis now has tangled messages about what it should be doing with a mess of forces being distributed all around the car, resulting in confusion from the driver, confusion from the chassis, overall loss of confidence and slower corner speeds. The driver is really going to struggle to not just access the available performance in the first place, but they're also going to struggle to be able to maintain that with the car dancing on the limit of that traction. So now let's consider a more stiffer chassis in the race car that's been better tuned in terms of the right spring rates on each corner and its dampers. And we've got something that approaches a much better front to rear balance. By that I mean it's less likely to understeer or oversteer in an unpredictable manner. So from the driver's perspective, that means they're going to input some steering or something into the chassis. The chassis is going to respond probably sooner and in a more reliable sort of a way, that the driver is going to be confident that another input that they may make is going to give a similar sort of result. That way the driver is able to get to that limit of grip faster and more reliably, and then they're also going to be able to maintain that the vehicle on the limit of that grip for longer. I guess out of this, the way I see all of this is my one sentence summary is that The suspension is really only ever going to be able to tune what the chassis is going to be able to transmit from one end to the other in terms of forces and how it's going to be able to reliably transmit the mass forces from the car to each of those contact patches. Now let's talk about the final chassis stiffness testing results. Remember the graph of the springs we had in parallel earlier, where we saw that the two springs, when they were connected in parallel, side by side, resulted in an overall stiffer spring. Well, that's pretty much what happened when we strategically added those bars into this stock MK chassis in parallel with all of the other bars. And by now, you're probably starting to see them all as springs, which is probably the right way of looking at it. So we added 9 springs or bars weighing less than 4 kilograms, which worked to increase the overall mass of the chassis by about 5%, but it increased the overall stiffness by about 230%. At the end of episode 7, we'd achieved about 4,027, I think, Newton meters per degree of twist as the spring rate for the chassis spring. And I mentioned back then that I might do some more testing with the floor panels in. In episode 2, you remember we actually added those floor panels and I retested after bonding those in with epoxy. Continuity is a difficult thing to manage with producing these videos. But anyway, I'm sure you're all over it. So I went to a bit of trouble to bond those floor panels in because I wanted to do the best that I could to really key them in and make them an integral part of the chassis. Epoxy, when it goes off, is very, very stiff, and the stainless steel rivets that I used then have quite a high shear stiffness. The overall result is I feel that I've done a decent job in fully integrating those two floor panels into the overall structure. Some research that I did in looking at all this suggested that the number seems to be roughly between about 6 and 10 times. So by that I mean that if you can get the chassis to be between 6 and 10 times stiffer than what the front and the rear suspension systems are, well then generally you're sort of in the zone of having a chassis that's going to be pretty responsive and more tuned to extracting the most that you can get out of your tyres. The results, as we saw with where I finally got to with this chassis and the floor panels bonded in, you know, we got an awesome result there. Over 5,000 is really, really high for one of these types of chassis. They're known to be light, they're known to be flexible. So I'm super happy with where we got to with all of that. I think at this point I've done pretty much what I can to set the rest of this project up for success when we come to driving it and really starting to tune it. There might be some other things we can do down the track, but super happy with where we are now. I hope you've got something out of this 3-part series. It was a significant part of this project for me, like it was about the major risk that I had for getting this car on the road, is achieving those results that I needed to be able to get it registered. So if you've stuck with it this far, congratulations for getting here. This has been a bit of a haul. There's a lot to unpack here, and I admit to knowing just the surface. There's so much more for me to learn on this, and there's probably areas in what I've been talking about today. But anyway, we'll fix that as we move on. Moving on to the next episode, finally we're going to be getting past the chassis stuff and getting stuck into the exhaust. This exhaust Lego, as I like to call it, has been here for far too long. It's had many, many iterations. Behind the camera there is a pile of lots of different varieties of this exhaust Lego that I printed and then worked out that it was wrong in some way. But we've got to a point now where we've got equal lengths on the primaries, and that's about the right length for what I think it needs to be for the tune that I want for this engine, mostly torque focused. So next episode is going to be on how I arrived at those lengths. We're going to start to look at the fabrication process for this exhaust, and hopefully in the next couple of episodes, maybe 3 episodes, get to the point where we've got the exhaust system completed and we can then start getting stuck into final bits and pieces to get this engine ready for first start. We've got a few things to do with the cooling system. Not too much, just a couple of things. We've got a couple of things to do with the wiring loom. I've got the stock MX5 wiring loom to drape over this chassis, and then hopefully hit the key and it'll just go, just like that. That's the aim. All right, that's the end. Catch you next time. Thanks for watching. Bye. Over the next few days, if you find yourself looking at springs and wondering whether they're in series and parallel, that's fine. Springs are cool.